Assalamu alaikum. Welcome to the next class. In this class, we'll start with the approximation that we usually do for our practical transmission line. In the previous class, we discussed about the long transmission line. We discussed about the surge impedance loading, uh, and incident voltage wave, reflected voltage wave, etc. Today, we'll start with the approximation. And the approximation, you know that we assume that the resistance of the series resistance of the transmission line is equal to 0 and shunt conductance of the transmission line is equal to 0. So in that case, when we do that, this ZC is equal to root of L by C, gamma is equal to square root of Y by Z, that is equal to J omega root of L and C, which is equal to J times beta. So in this case, alpha is equal to 0 and beta is equal to omega root of L and C. Now, let us see what will happen to the A, B, C, and D. A and D will be equal to cos hyperbolic J beta L. How? Because we know that cos of alpha is equal to 0. It is cos hyperbolic gamma L. Gamma is equal to alpha plus J beta L. Where alpha is equal to 0, it comes out to be cos hyperbolic J beta L, which is equal to cos of beta L. It is actually because of this cos alpha plus J beta L is equal to cos hyperbolic alpha L cos beta L plus J sin hyperbolic alpha L sin beta L. We have already discussed this formula. So when alpha is equal to 0, cos hyperbolic alpha L will be equal to 1 and sin hyperbolic alpha L will be equal to 0. This term goes and this is 1 into cos of beta L, it will be equal to cos of beta L. So B is equal to ZC sin hyperbolic gamma L, that is equal to J ZC sin beta L. So in this case, sin hyperbolic gamma L will be equal to J sin beta L. You can see it from here. Sin hyperbolic gamma L will be equal to sin hyperbolic alpha L cos beta L plus J cos hyperbolic alpha L sin beta L. For alpha is equal to 0, this term will be totally 0. This cos alpha L will be equal to 1, it will be equal to J sin beta L, that is J sin beta L. Similarly, C will be equal to sin hyperbolic gamma L divided by ZC, that is this term will be equal to J sin beta L divided by ZC of this on. So when the approximations are done, ABCD parameters will be like this. Now let us move to the wavelength of the transmission line. What is the wavelength of the transmission line? We know that this beta L is the total angle from receiving end to sending end. That is this beta L is the angle of the receiving end that it leads with respect to the beta L is the angle of the sending end that it leads with respect to the sending end. Or we can say this sending end voltage leads to the receiving end voltage by beta L. So if this L increases in such a way, it increases in such a way so that this total angle becomes 2 pi. So when this angle becomes 2 pi, because this angle is itself dependent upon the value of the length. Beta is constant. If an L increases, this will also increase. So if it increase in such a way so that at one point it will become equal to 2 pi. And at that case, this L may be called as the wavelength of the line. When this angle is 2 pi, we say that the one complete cycle is complete. In that case, one complete cycle is completed and L will be the wavelength of the line. So because after this, it will repeat its cycle again and again. So at this point, the length of the line is equal to the wavelength of the line. That means this beta into length, that is length will be in a wavelength, that's lambda is equal to 2 pi. That's what I have written over here. Beta into lambda is equal to 2 pi, or lambda is equal to 2 pi by beta. That means the wavelength of the line will be 2 pi by beta, and its length will be its units will be of course meters. So but beta is equal to omega root of LC for a lossless line. So omega is equal to 2 pi f, 2 pi cancel out, be equal to 1 divided by f root of L by C. And we also know that this 1 by root of LC is equal to V, so it will be equal to V by f. So lambda is equal to V by f, where V is equal to 1 by root of LC. So the is the velocity of the propagation of the wave. So this is actually equal to the velocity of the light. It comes out to be 3 into 10 to the power 8 meters per second. We have already calculated it. So it comes to be 3 into 10 to the power 8 meters per second. Now, lambda will be equal to 3 into 10 to the power 8 divided by 50 when the system is running at 50 Hertz. it is 600 kilometers for 50 hertz line. So lambda will be equal to 300 times the power 8 divided by 60, which will be equal to 5000 kilometers for 600 hertz line. That means the angle will change from sending end to receiving end. It will change its direction when the length of the line is 6000 kilometers for 50 hertz line and 5000 kilometers for 60 hertz line. So in that case, you may understand, you will get an idea that when will this angle, or we can say what should be the length of the line, so that this the angle of the sending end and receiving end should be equal to 2 pi. That means they are coincident again, they are in phase. Now let us move to the equivalent circuit model of the long transmission line. Since we don't have any circuit model of long transmission line, we may try to make some equivalent circuit which may represent the input-output relationship of the long transmission line. Let us say we'll start with a pi equivalent model. Actually, this is not the exact model, or we can say these are not the exact values of z, y dash, z dash. I have represented them with z dash, y dash, and y dash by 2, so that in place of long transmission line, I will place this model in such a way so that this input-output relationship remains the same. That means for a long transmission line, if VR, IR, VSIS have some value, and I replace that long transmission line by this pi equivalent model, and I am getting the same values of IR and VR for the same values of VS and IR. That means this circuit will be the equivalent circuit of the long transmission line. I will try to find out the values of z dash, y dash, and so that these parameters, input-output relations, remain the same. So I will come to know, I will come to that point. Why do we require this if we already have the mathematical model of the long transmission line, that is this? So I will let you know that. So for pi model, we know that this Vs is equal to 1 plus y dash z dash by 2 Vr plus z dash into IR, because for pi network, we know that this is the relationship between Vs and Vr and IR. Similarly, Is is 1 plus y dash z dash by 4 into y dash into Vr plus 1 plus y dash z dash by 2 into IR. So this relationship we have already calculated in terms of medium transmission line for pi and T model. So this is for the pi model. This is again a pi model, but instead of z and y, we have represented here z dash and y dash, just to differentiate them from the actual value of the series impedance of the line and shunt impedance of the line, because they are not representing the actual values of the shunt admittance and the series impedance. So for long transmission line, we know that Vs is equal to cos hyperbolic Vr plus Zc sin hyperbolic gamma L into IR, and Is is equal to sin hyperbolic gamma L Vr divided by Zc plus cos hyperbolic gamma L into IR. By comparing these four equations, that means cos hyperbolic gamma L will be equal to this term, and Zc sin hyperbolic gamma L will be equal to this term, and sin hyperbolic gamma L Zc will be equal to this term. I'll only use this term, that means this and this to calculate this y dash by 2 and z dash. So this, by the comparison, I have calculated the equations. I computed the equation that cos hyperbolic gamma L will be equal to 1 plus y dash z dash by 2. Z dash is equal to Zc sin hyperbolic gamma L. By using this, one parameter is already done. That means Z dash is equal to Zc sin hyperbolic gamma L. So from this, cos hyperbolic gamma L minus 1 will be equal to y dash z dash by 2, or cos hyperbolic gamma L divided by z dash will be equal to y dash by 2. So this z dash is actually equal to Zc sin hyperbolic gamma, and that means this y dash by 2 is equal to cos hyperbolic gamma L minus 1 divided by Zc sin hyperbolic gamma L. Now I will convert them into the half angle formula. We know that for a normal cos, 1 minus cos of theta is equal to twice sin square theta by 2, but for hyperbolic it is other way around. Cos hyperbolic gamma L minus 1 will be equal to twice sin square gamma L by 2. Similarly, for this sin hyperbolic gamma L, it will be similar to that, the normal sine. It will be equal to twice sin hyperbolic gamma L by 2 cos hyperbolic gamma L by 2. So converting into that, that means cos hyperbolic gamma L minus 1 will be equal to twice sine square gamma L by 2. ZC is as it is. This will be converted into half angles. This will be twice sine hyperbolic gamma L by 2 cos hyperbolic gamma L by 2. Here 2 and 2 will cancel out. 2 and 2 will cancel out. Sine hyperbolic here and 1 sine hyperbolic at the numerator will cancel out. This sine hyperbolic gamma L 1 will remain there. That sine hyperbolic gamma L by 2 cos hyperbolic gamma L by 2 will be equal to tan hyperbolic gamma L by 2 divided by this ZC. So in that case, so this is equal to YC tan hyperbolic gamma by 2. Okay, so that means y dash by 2 is equal to YC tan hyperbolic gamma by 2 divided by 2. So we have already calculated why YC is equal to 1 by ZC, that is equal to root of C by L, that is the inverse of the ZC. So the series parameter, that is this Z dash, will be equal to ZC sine hyperbolic gamma L, that is ZC sine hyperbolic gamma L, and this y dash by 2 is equal to YC by 2 tan hyperbolic gamma L by 2. This is also YC by 2 tan hyperbolic gamma L by 2. So this actually calculation of the equivalent pi network for the long transmission line is used for the simulation purposes. Because in simulation purposes, when we use the long transmission line, we don't have the actual network or actual circuit. So when we use the circuit, we have to use this circuit, and the parameters of this circuit are to be calculated like this. So when we calculate the parameters like this, in that case, then we can use this for the simulation purposes. Similarly, by using the similar analysis, you can also calculate the T equivalent model. In case of T equivalent model, we have Z dash by 2 y. That means all the shunt capacitance are placed at the middle of the line. So when they are actually calculated in terms of ZC and YC, so this ZC by 2, Z dash by 2 is equal to ZC by 2 tan hyperbolic gamma L by 2, ZC by 2 tan hyperbolic gamma L by 2, where Y dash is equal to YC sine hyperbolic gamma L by 2. And I have told you in the previous classes when we discussed the medium transmission line, the mostly pi network which is usually used because of its simplicity, and we have only one unknown node, that is here, as compared to two unknown nodes. One is this and one is this. So mostly we are going to use this as compared to this. But I have shown you both the networks so that you may understand how to calculate the parameters of transmission line. Now coming to the power flow through the transmission line. This is also an important topic. Let us say we have a source, we have a bus, two buses which are connected through a transmission line, and we have a load. The load voltage, that is the receiving end voltage, is given as VR at an angle of 0. We are taking this as a reference, and Vs is taken at an angle delta with respect to this VR. So the receiving end is getting the receiving end complex power, which is equal to PR plus JQR, where PR is equal to receiving end real power. This is the receiving end reactive power. Similarly, this S is the sending end complex power, PS is the sending end real power, and QS is the sending end reactive power. When we know in terms of the voltages and currents, this SS, that is the complex power at the sending end, will be given as Vs into Is star, which is then equal to PS plus GQS. And SR will be equal to VR into IR star, which will be equal to PR plus JQR. So we'll first try to find out IS and IR in terms of VR and VS to get the values of this SS and SR. So we'll get this IR and IS from the ABCD parameters in terms of VS and VR. So here it is very simple. VS is equal to AVR plus BIR. So from here, Vs minus AVR is equal to BIR. So that means IR will be equal to Vs by B minus A by B into VR. That is over here. So IR is equal to 1 by B into Vs minus A by B into VR. So I have got the value of IR in terms of VS and VR. Similarly, IS is equal to CVR plus DIR. So it is equal to CVR plus D into 1 by B into Vs minus A by B into VR. This is actually the value of the IR, which is taken from here and placed over here. So multiply this, it will be equal to, I will take VR common. So VR has two terms, one is this C and then minus AD by B. So it will be equal to C minus AD by B into VR plus D into B into Vs. D divided by B into Vs. I will write down first this D by B into Vs, that is D by B into Vs, and then multiply it, cross multiply, it will be equal to BC minus AD divided by B into VR. That comes out with this. We know that from the reciprocity of the transmission line, BC minus, sorry, AD minus BC is equal to 1, or BC minus AD is equal to minus 1. So this will be equal to D by B into Vs minus 1 by B into VR. So Is is equal to D by B into Vs minus 1 by B into VR, because AD minus BC is equal to 1. So here also we get Is in terms of Vs and VR. Since we know that this A, B, C and D, all of them are complex numbers, so let A is equal to magnitude of A at an angle of alpha, B is equal to magnitude of B at an angle of beta, D is also same as that of A, and Vs is equal to Vs at an angle of delta. VR, as we know that we are taking that as a reference, VR will be equal to VR at an angle of 0. We don't have to define that because its angle is 0. So therefore IR is equal to, which is over here, that is equal to Vs at an angle of delta divided by B at an angle of beta minus A at an angle of alpha into VR, that is angle 0, divided by B at an angle of beta. So when you take this angle common and take it at the numerator, so this will be equal to Vs, its angle is delta, beta, its angle is, B, its angle is beta. So when you take it to the numerator, they will be subtracted. That means this will be equal to Vs by beta into delta minus beta. Similarly, for this case, it will be equal to angle of alpha, angle of VR minus angle of beta. Since angle of VR is 0, it will be equal to angle of alpha minus beta. It will be equal to A by B VR angle of alpha minus beta. So finally, IR will be equal to Vs by beta. So when I write it in this form, I have dropped the magnitude sign. So it means that it is a magnitude. From here on, I am only using the magnitude and I am taking the angle separately. So it will be equal to Vs by beta into delta minus beta minus A by B VR, A by B into VR angle of alpha minus beta. Similarly, Is will be equal to, from here, D by B, which is actually equal to A because D is equal to A, D by B Vs. So A has an angle of alpha, B has an angle of beta, Vs has an angle of delta. So when you take to numerator, it will be equal to delta plus angle. This A, alpha will be plus angle and beta will be minus angle. It will be equal to delta plus alpha minus beta. Similarly, for this case, it will be equal to VR has angle of 0, beta, B has angle of beta. When you take it to the numerator, it will be equal to at an angle of minus beta. So calculating the complex power at the receiving end. So SR is equal to VR into IR star. So IR star will be now, it will be same, but the angles, the magnitude of, sign of the angle will be changed. It will be now beta minus delta. This will be now beta minus alpha. This will be this angle will be beta minus delta minus alpha. This angle will be plus beta. So when you calculate the receiving and complex power, so you multiply IR star by VR, so it will be equal to VR Vs with beta, that is this, beta minus delta, angle sign will change, and A by B, VR square, beta minus alpha, angle will change, angle sign will change. Now complex power at the sending end, it is equal to Vs into IS star. Is is this, so Vs will be equal to Vs into delta, and you have to change it. It will be equal to delta minus alpha plus beta. That means delta and delta will cancel out, to be equal to beta minus alpha. That is beta minus alpha. Minus Vs by beta. This will be actually plus beta, and Vs will have delta. That will be equal to delta plus beta. So this is the complex power at the sending end, and it is in terms of the polar form. So when you try to write it in terms of the rectangular form, you will see we have a real part that is equal to Vs VR by beta cos of beta minus delta minus A by B VR square cos of beta minus alpha, that will be equal to PR. Similarly, QR will be the Imaginary part of the SR, that is equal to Vs VR by beta sine of beta minus delta minus A by B VR square sine of beta minus alpha. PS will be equal to A by B Vs square cos of beta minus alpha minus Vs VR by beta cos of delta plus beta. This is the real part of the SS, real part of this. So imaginary part of this will be equal to Qs, that is A by B Vs square sine of beta minus alpha minus Vs VR by beta sine delta plus beta. So these are actually four terms, four quantities, two at the receiving end, two at the sending end. So now we will try to see what will be the condition for the maximum receiving end power. The maximum receiving end power will occur when delta is equal to beta. In that case, when delta is equal to beta, this term will be equal to 1. So it will have a maximum value. So when this is equal to 1, and this is equal to 1, PR max will be equal to Vs VR by beta minus A by B VR square cos of beta minus alpha. It remains as it is because it is independent of the delta. And when this occurs, this QR will be equal to this QR when delta is equal to B, and this term will be equal to 0. This term will be equal to minus A by B VR square sine beta minus alpha. That is this. That means in this case, when this happens, when QR is minus, that means receiving end is supplying the reactive power, or it draws the leading MVAR. When we're supplying the reactive power, it means power factor is leading. It means it is a capacitive load. It means the load should supply the reactive power. We can say generally load must draw this much, that is this much of the leading MVAR in order to receive the maximal real power. So maximal real power will not be achieved like this. It has to be achieved when the load is to be supplied some local reactive power at the receiving end. That means load should be supplied the reactive power, and load must be capacitive, and the power factor will be leading. It will be at the receiving end. Now for short transmission line, we know that A is equal to D is equal to 1, B is equal to Z at an angle of theta. I will write in terms of the polar form. So PR is equal to VSVR by Z cos of theta minus delta. So B is equal to Z, it will be equal to VSVR by Z cos of beta minus delta. It remains as it is. And this will be equal to A is equal to 1 VR square by Z, B is equal to Z. B is equal to Z cos of beta minus alpha, but beta is equal to now theta. That is the impedance angle of this Z. That is what I have written over here. You can see cos of theta. QR is equal to similarly VSVR by Z sine of theta minus beta, theta minus delta minus VR square by Z sine of theta. For PR to be maximum, theta should be equal to delta. That means PR maximum will be equal to VSVR by Z, VSVR by Z. That is, this will remain as 1 minus VR square by Z square into R. I actually changed this. This cos theta will be equal to, from here impedance triangle, cos theta will be equal to R by Z. So it will be equal to R by Z. Here it will be R, here it is Z, Z and that will be Z square. It will be equal to VR square by Z square into R. So for practical transmission line, or we can say lossless transmission line, R is equal to 0. When R is equal to 0, you can see that this Z is equal to X, they will be coincident, and theta will be equal to 90 degrees. Theta will be 90. That means, and this is equal to cos of 90 minus delta, it will be equal to sine delta, and this term will be equal to 0. So that means PR will be equal to VSVR by X sine of delta. Now Z will be equal to X, Z will be equal to X. And PR max will be equal to VSVR by X, because delta will be equal to theta, that theta will be equal to 90, that sine delta will be equal to 1. So PR max will be equal to VSVR by X. This is the most commonly used formula to calculate the maximum power transfer. So similarly for QR, it will be equal to VSVR by X cos of delta minus VR square by X. It is derived from his VS by, this will be X, this will be 90 minus delta, that is cos of delta, minus this VR square by X sine 90 will be equal to 1. This will be QR. Now let us look at the QR. This cos delta has a practical value from, we can say delta has a practical value from 5 degrees to 15 degrees. 5 degrees to 15 degrees, that means we can assume this cos delta to be equal to close to 1. That means this cos of this QR will be then equal to Vs VR by x. This is 1 minus VR square by x. That is what I have written over here. That is Vs VR by x minus VR square by x. Taking this Vs by x common, sorry, VR by x common, it will be equal to Vs minus VR. This is actually magnitude because we have taken a consideration of all the angle. This is not a phasor. So Vs minus Vr will be the voltage difference from sending end to receiving end. That will be delta. It's denoted by the delta V. So we can say for a constant Vr and x, this QR will be proportional to change in the voltage from receiving end to sending end. This is one more important result. You need to remember this because based on this we can derive delta V, or based on delta V we can derive for QR. From this relation, that is this relation, this PR is proportional to sine delta, and it is proportional to delta when delta is very small, that's a practical value, and QR is proportional to delta V. That means they are independently proportional to their individual parameters. We can say that this PR, real power, depends mainly on the delta. It does not depend upon the change in the voltage, while QR depends upon the delta V, where it does not depend upon the value of the delta. And Pmax occurs at when delta is equal to 90 degrees, that is equal to Vs VR by x. I have told you just before this slide. And Pmax can be increased by increasing the voltage, that is Vs and Vr, and it can be also increased by decreasing this x. So by using bundle conductor, this x may reduce, which in turn increase the power transfer capability of the transmission line. Now coming back to this reactive power, the lagging reactive power PR, this should be actually QR, is proportional to delta V and is independent of the delta, as delta is very small practically. So this lagging reactive power is proportional to delta V. That is actually the written statement of this this mathematical relation. So what does this mean? It demands, if demand for lagging reactive power is large, that means delta V will be large. So when this is large, delta V will be large. For a constant Vs, this has to drop very much to keep this in, to match the demand of this QR. So that is what practically happens when reactive power demand increases, VR drops sharply. To make the voltage profile good, VRs, that means volt ampere reactive, that means reactive power has to be supplied locally. This is very important. This derivation can also be derived from the simple derivation that we have already derived. This is actually the approximation. We know that this delta V is equal to IR into R cos of theta. This is the derivation we have derived for the voltage regulation, plus IR into X sine of theta. In that case, we have actually written that delta V by V is equal to IR R cos of theta plus IR X sine of theta divided by V. But here I am taking only the numerator, it will be equal to this. So multiply both sides by VR, we get, so delta V into VR will be equal to VR into IR into R cos theta, that is this term, plus VR into IR into X sine of theta. For lossless line, R is equal to 0. That means this term will be vanished. It will be equal to this term. So I will write it as like this. So delta V is equal to, this will be in denominator, VR IR sine of theta into X divided by VR. So this VR IR sine of theta is equal to QR, that is the reactive power, and this is its X and VR. So QR will be equal to delta V into VR by X. So QR is equal to VR divided by X into delta V. So by using this formula also, voltage regulation formula, we have also derived the value of the QR. So there are two important things, that this voltage drop, or we can say voltage drop from sending end to receiving end, depends upon the how much reactive power has to be supplied to the sending end, and This real power depends upon the delta, that is the angle between the sending end and the receiving end. Okay, thank you. I will stop over here.